Yeah, good morning. Good afternoon, everyone. Thank you for joining the National Stock Assessment Science Seminar Series. My name is Bailey. I coordinate this monthly seminar series highlighting interesting advances and topics in stock assessment science. Today, we have Dr. Alan Chen with us. Alan received his PhD in economics from the University of Washington, and now he works as an economist in the Economic and Social Science Research Program at the Northwest Fisheries Science Center. He's particularly interested in integrating models of fisher behavior into our understanding of biological systems. During today's seminar, we'll see how economists count fish. So now, without further ado, I'll pass it over to Alan.
Thanks, bye. Okay. If there are any technical issues, I hope someone will speak up. Hi, everybody. I'm Alan. I am an economist at the Northwest Fisheries Science Center, and today I'll be talking a little bit about how economists would count fish. This is some joint work with Cole Monahan, Owen Hamill, and Alan Haney. And so the title is a little bit misleading since two of those are stock assessors, but we are coming at this from the point of view of an economist, I think. And I was digging through some old slides, and I'd given a version of this talk at an economics conference at some point to economists, and I had started it off with this slide, where I told all the economists that stock assessments are useful and important. And then I went on and explained very vaguely what stock assessments were and what they were used for. This seemed wholly inappropriate for a national stock assessment science seminar. So instead, we're going to switch it up and go with economics is useful and important. And when people think about economics, a lot of times they think about dollars. When I get questions from outside the agency, typically it's someone asking me, there's some policy and they want to know like how many dollars is that? How many jobs is that? And that's also important and it's part of economics. But I think when you ask an economist what they're interested in, they might tell you that they're interested in human behavior. We are curious about what makes people tick. What are their preferences? What do they care about? And then how do they make decisions given those preferences? What are the trade-offs that they have to make? And this is a theme that we'll be going into more today, thinking about, well, if we understand what their preferences are and how they make these trade-offs, can this essentially help us improve stock assessments? The modeling framework we're going to be using is stock synthesis. I won't belabor the point to a bunch of assessors, most likely, but stock synthesis is a statistical age structure model. It takes in a bunch of data, non-comprehensively, age and length comp data, but also a time series of abundances. And that's the primary data that we're going to be playing with today. We're going to be using a specific package that is SS3Sim. And this package basically lets us run simulations using stock synthesis. So given some sort of process error, it's like a Monte Carlo type framework where we can run a bunch of iterations and look at the variation in output. So back to abundance indices. Typically, I think the gold standard from my understanding as an economist is that fishery-independent data is what stock assessors like to use. For example, those collected by fishery-independent surveys. A census for fish is some ways where we go out and it's standardized and they have these stations and they're going to sample the ocean and sort of figure out how many fish are in the ocean. If assessors do need to use fishery-dependent data, and I'm not trying to set up a straw man here too much, but I think it's well known, I'm preaching to the choir, that fishery-dependent data needs to be treated with care. And assessors are well aware that the data is selected in a way. And as an example, I liked this news article from a couple years back. It's about the Gulf of Maine. Little hope in latest evaluations of codfish. And I like this article because they went and they asked a stock assessor, and then the reporter went and talked to a fisher as well. And when they asked the assessor, how are the codfish doing? The assessor told them the assessment concluded each species is overfished, still experiencing overfishing, truncated size and age structure, no signs of incoming recruitment, continued low survey indices. Sounds bad. And then they went and talked to a fisher, and the fisher was like, well, for many years now, fishermen have been experiencing a far greater scale of abundance for many ground fish stocks than what is being reported by those assessors. And I think this sort of divergence is something we hear often, where fishers will say, well, we're out there every day and we think the fishery is doing great. And so why is there this divergence? And in what way could both of them be true? Or in what way can we explain both of these observations? And intuitively, if it's because fishers are skilled at fishing and they're only going to go to locations when and where the fishing is good. If the fishing is bad somewhere, they're not going to waste their time and their fuel and their energy and their effort fishing there. So when they go fish somewhere, the fishing is good because they're good at it. And it's this specific type of selection and error that we're going to investigate today, where fishers might have some sort of information that allows them to be good at fishing and select where they go. And because of that, the sample of observed catches that we see is biased in some way. So back to stock synthesis. Most of the time, we don't use these fishery-dependent indices because of the way it's selected, or they have to be very careful about correcting or standardizing them. And there are a number of standardization methods in the fisheries science literature. I don't mean to say that this is a topic that hasn't been investigated. And what we're interested in is, can understanding the behavior, the preferences of fishers help us count fish? And in that way, this data tends to be, at least in the United States, I would say widely collected. We get observer coverage on a lot of vessels in our fisheries. So this is data that we're collecting anyways, a lot of times for regulations or for management purposes, but we might not be using in assessments. And then there are also these other fisheries where maybe we don't have the luxury of fishery-independent surveys. So these data weak situations where we need to use fishery-dependent data, for example, with highly migratory species where it's not feasible to sample such a large area. All right, so this is our workflow in SS3 Sim. We'll be going back to a version of this slide frequently, I hope, throughout the talk. We are going to create an operating model, an OM, in SS3 Sim. This is that biological model. We can give it some biological inputs about recruitment and mortality, and we'll go over that in a little bit. From that biological model, it will give us a bunch of other data that we can use in our estimating model. We don't touch that. That's just part of the normal SS3 Sim process. What we are going to grab from that OM is the true abundance. So the biological model is going to have some true abundance in every year, right? And so that true abundance, we're going to pass to some fishery model. And that fishery model is going to generate fishery data for us. And that fishery data, basically catches, we can then take those catches and fit that in some econometric model to create a corrected abundance index. Or maybe we don't correct it. We'll take a look at both, and we can pass that index to the estimating model. So this would comprise one single iteration in SS3 Sim where you have some process error. We have the state of the world here. We have a bunch of what the truth is. We pass it through, and then we're going to do this, 100 or 200 times to see what it how it might vary depending on how the randomness changes over the bunch of iterations. For our OM, we have just highlighting a few of these inputs, and at the end, if there's interest, I have a larger table. But we have linearly increasing fishing mortality that ramps to FMSY. It's approximately 0.17. Natural mortality is fixed at 0.2. Fishery and survey selectivity here is double normal, but calibrated to be logistic. We have von Bertalanffy feed growth and Beverton-Holt spawner recruitment. And our process error is going to take the form of independent log normal random deviations around median recruitment. And so in every iteration, the OM is going to pop out some truth for us. We take this truth, and then for the fishery model, we take the abundance in every single year. And so we only get, this is year 88, and we know what the abundance is. We're going to distribute that abundance over space in some manner, according to one of 4 different scenarios, but the underlying mechanism is going to be very similar over all 4. Then, given however we've distributed the abundance, we're going to generate catches. So then in the fishery model, the abundance has been spread out over space. Fishers are then going to say, all right, where do I want to go fish? For a given haul occasion, I get to choose some place that I want to go fish. They make catches, and then we see what they caught. Then the same way as if we had observer coverage, we write those catches down. They're recorded for us. The fishers are going to keep doing that until the sum of all the catches equals the total catches in the OM. So whatever the OM said the catches were. All right. So for the fishery model, the idea is, here is just an illustration. We split up space into 4 discrete areas. So there are 4 different areas, just as an illustration, where fishers could go. And a bigger fish here, maybe there are more fish in that area, smaller fish, there are less fish in that area, right? So how are we going to split up the abundance across space? What we're going to do is assign each one of these areas a beta. And the beta just represents some sort of proportional abundance. So J is the jth location. If we had 4 locations, the big J equals 4. Y is a given year. And then here, A superscript T is the true abundance in any given year. Mu sub A is the mean abundance over our whole time series. And so what we're really doing here is we're just scaling the proportional abundance up or down depending on whether or not the true abundance is bigger or smaller. And then the abundance for the fishery in any given year is just that scaled beta, but summed over all locations. And the key here is that the sum of the betas over all locations is equal to some constant. And so as an example, let's say that abundance is fixed. In each area, the abundance is the same in every single year. Proportional abundance is the same in every single year. 0.8, 1, 1.2, 1.4. And in that way, you can see that if this were the case, the only thing driving changes across years is that true abundance scaling factor, right? Because the betas aren't changing over years. So the only thing that's changing over years is the true abundance from the OM. And so we want to make sure that the only thing driving abundance, right, in our fishery model is coming from the OM. So if there are a couple locations, the fisher decides where to go fish. Maybe they decided this little area here with the yellow vessel, right? We'd see the catches. The problem is that there were some catches, right, fish in these other areas, but we don't get to see what those abundances or catches would have been, right? We only see the catches where the fisher chose to go. And so typically, and this is where I think the economics of this problem overlaps with the fisheries science part of the problem, is that usually, as an economist, if I want to know, well, where are they going to choose where to go? What are the things that are important to them? I need to know what the catches are. at all those locations as well. Like what would they have caught, right? And usually we would have to make some sort of estimate or proxy of expected catches out of these other locations to use in our discrete choice problem. And a discrete choice problem is just this question of we split up this area into discrete areas and we want to know where they choose to go. And this type of problem is fairly popular in fisheries economics. It has been used to investigate a number of questions, such as the willingness of fishers to avoid common pool bycatch. For example, if each area has a different level of bycatch, are they avoiding certain areas with higher bycatch species? Are they sharing information? Are fishers going to areas where other fishers have gone before, or if there are a large number of fishers there already? Or the effect of spatial closures. So if I had to close off an area due to regulations or wind farms or anything else, probabilistically, where else would the fishers go instead? And ultimately, this problem is popular in fisheries, but the canonical example, I believe, is when someone wanted to investigate the sighting of BART stations, the San Francisco public transit line. So it is fairly popular, I would say, in the economics discipline as a whole. So for our fishery model, what we're going to do is we are going to start with a pretty stylized model where catches here, Y, for the ith fisher, for the teeth haul occasion, for the jth location, is just going to be a function of our proportional abundance for that location, and then some covariates. Here we're going to say it's vessel tons, so a larger vessel might catch more fish. Our fishers are going to know basically what the catches are. And here I kept xi in here because I'm going to use vessel tons for illustrative purposes, but you could think that whatever you think catches are a function of, whatever covariates you think should be in this catch function, they should be. And we'll revisit that a little in a couple more sentences. This u parameter is the unobserved sort of heterogeneity that the researcher doesn't see, right? This is the stochastic term that represents any sort of influences that are going to influence catch, but we can't capture in our model. The fishers in this model are going to know what the U term is, but we could generalize it such that there's some term where it's a superscript F that they do know and maybe that they don't know. Right? But for our purposes, we're just going to say they see the stochastic term, they know their own tons and the proportional abundance, so they know what the true catches are going to be when they choose, well, where do I want to go? Right? And the idea behind the stochastic term is that there's some information that fishers might know of that researchers don't. For example, if fishers are fishing on a school of fish, an aggregation, and that aggregation is moving to a new location, even though the fishers never fished there before, they might know that catches are good there, right? Because they're just sitting on this aggregation, following it across space. Or fishers might be skilled, or they might share information in some way, where someone else calls them up on the radio and says, I'm fishing over here in location 2, and the fishing is great over here. Come over here, right? There's no way that as a researcher, we might have that sort of information about how that influences their expected catches. So this beta j times tons term here is essentially just a fisher-specific average, right? It's just average catches, and then for any given haul, it might be bigger or smaller than the average depending on the realization of our stochastic term. I would note that this is pretty stylized. There are more nuanced methods as far as how we can specify expected catches in the fisheries literature. For example, it's popular to use lagged catches or catches from last week or from a month ago or some sort of combination of those. But here we're just going to have basically average catches, and then in any given haul, it'll be bigger or smaller, and that error term is going to be distributed normal mean 0. So notably, right, if I got to see all the catches, that error term essentially cancels itself out. And then vessel tons is going to be distributed uniform 1.5, and in any given haul occasion, basically we're just going to kind of pull a random vessel and be like, this is the vessel that's fishing. Now, for the fisher's choice problem, what we're going to say is the fisher is going to choose a location, the jth location, as long as their utility u is greater at that location compared to every other location. So all other locations m that aren't j. Now their utility u, the ith fisher for the teeth haul, jth location, is going to be a function of their catches. And then this is just their alphas and marginal utility from catch. So you could expect if we think that they like catches, then alpha is going to be positive. And here we've just substituted in catches, so beta tons plus our stochastic term. And then their costs are going to be a function of distance, where maybe they don't like to travel. Notably, you can see when we substitute in catches, they care about catches, but catches are a function of u, and because they're more likely to choose locations with larger utility, they're also more likely to choose locations with larger catches and a larger realization of that error term. Here, when we pull some horsepower in every single haul, it's going to be uniform 110, and basically a larger vessel may care more or less about traveling distance. Our unobserved heterogeneity in our utility function is distributed Gumbel or type 1 extreme value. There's a closed form. The probability of selection has a nice closed form solution when we make that assumption. All right. So given that in a bunch of hauls, right, we pull a bunch of data, we pull our catch error, we pull our utility here, and then we pull the horsepower in tons. They decide where to go. We see the catches. They keep going until it equals total catches from the OM. How do we estimate beta, right? Or how do we estimate what the average catches at a location actually were? You could just take all the catches and average them. Essentially, that'd be the same as if we wanted to get an estimate for beta hat here, right? So if we had an estimate for beta hat and we multiplied it by our covariance, since we think catches are a function of vessel tons in our data generating process, we could get an estimate for y hat, an estimate for catches. The issue at hand, of course, is that we are worried that, well, what if the realization of u here is correlated with selection? Because as we saw, they're more likely to choose a location with higher utility, which means larger catches, which means larger u. Y tilde here is the observed catches that the researcher sees, right? And that's going to be a function of proportional abundance, but also potentially the conditional error, that is the mean error conditional on actually observing catches, right? And if this conditional error term doesn't equal 0, then when we regress catches on covariates such as tons to get our beta hat, and then we use that beta hat to construct a counterfactual or an estimate of catches, we'll end up with both biased betas and biased estimates of catch, right? So in this example, we would take our observed catches, regress them on tons, get a beta hat, use that beta hat, get an estimated catches, but we might run into problems. And as an illustration, let's say we had a single location here, right? Example sampling process for some arbitrary location. We had 10 different observations here, and then in any given observation, because of that realization of u, the catches might be bigger or smaller, right? And in a given day, fish maybe moved down there, and a different day they swam somewhere else. And so the catches might have been bigger or smaller at that location for any given observation. We don't get to see every single one of these observations, though, because we only get to see the observation when the fisher goes there. If we then take the sample of catches that we actually see, let's say we take that sample, we create an estimate for average catches. We typically denote estimates with a hat, as is common. That estimate tends to be biased by the expected value of the error term conditional on actually observing catches. So what we do, we build on a method to basically estimate corrected catches. And this is some work by Gordon Dahl that was looking at how people chose where to move in the United States, like Georgia versus California, depending on their wages. The literature we're drawing from is even further back than that, where we're looking at essentially the canonical example is looking at the effect on wages depending on gender. So, for example, if you're male or female, I see how much you made, whether you're male, whether you're female, and we want to see, well, how does that affect your wage? The problem in that example is that if you're entering the workforce as a female, typically, at least previously, but maybe even now, I'm not so familiar with the more recent research, you only did so if your wages were expected to be higher, right? So you also saw a selected sample of wages. Those estimates tend to be higher and the wage gap was underestimated. Our intuition is somewhat similar here. We only see them go to a place where when catches are good, right? So we sort of overestimate what the catches are going to be, and we believe that catches are better than they actually are. So what we do is essentially we still have our catch regression, observed catches on the left-hand side, our covariate tons. We want to estimate beta j. What we do is we include a polynomial approximation of that conditional expectation term. So that expected u right here, conditional on observing catch. And that polynomial is just a function of the probability of moving to that location. And so we have we want to estimate the beta associated with our covariate, a number of coefficients in that polynomial, and then we also create a different polynomial depending on whether they're whether they're choosing to stay at a location or whether or not they move to that location from a different location. But essentially, this polynomial approximation, we're taking advantage of some previous work that tells us that the conditional error term can be written as an invertible function of the probability of selection. And more intuitively, we can think of this as if the probability of going to a location is fairly small, and I see them go there anyway, and they had really big catches, that might tell me a little bit something about, well, what was the realization of u there, right? It might have been surprisingly high for that particular haul example. And if there's interest, I'd be happy to go into the methods a little bit more here. The nice bit about this is that by including the polynomial approximation, the remaining error is then mean zero in the conditional sample, and then we can essentially get unbiased estimates of beta hat in our catch regression. All right, this is almost the end of ugly economics, but I included this just so my stock assessor friends might feel at home. Here's a nice big likelihood. And what we're going to do is essentially jointly estimate the probability of seeing the catch that we did and the probability that they chose location together. And this first term here is just the catch equation. We assume that our error term was normal, right? So here's a normal likelihood. We have our observed catches, tons, and then our polynomial approximation. And we're going to jointly estimate that with the probability of selection here. And this term is the probability of selection that falls out because we made the assumption of the type 1 extreme error. And so we want to estimate both the betas in the catch equation and the polynomial approximation, but they're also free here in the probability of selection, and we're going to jointly estimate it together. All right, so reviewing real quick, what we did was we took the abundance and from the OM in every single year, right? We're going to distribute it over space in some way, and the scenarios are coming up after this slide. By doing so, fishers get to choose some area depending on that process we described, where they're going to choose a utility that's highest in any location. They choose a location, we see their catch, we record those catches. That catch includes some sort of stochastic term that the fishers know that we can't really capture. Fishers do that until the sum of catches equals the total catches from the OM. Then we're going to take all those catches and we're going to estimate the abundance in that year by estimating the betas, and then we essentially sum the betas. There should be some, you can weight it by area, but all our areas are going to be the same size, so we'll abstract from that a little bit. Then we take that abundance, and then we can pass it to the estimating model along with the rest of the stock synthesis data that's created by the OM. All right, scenarios. We have 4 of them. This is the first one. It is very similar to what we've basically been describing. Abundance is fixed. A darker area here is greater catches. We have 9 different locations, 1, 2, 3, 4, 5, 6, 7, 8, 9. The green numbers are the number of observations that we ended up seeing in a given year. And we also included some hypothetical example haul. So this is a single haul occasion. The fisher gets randomly placed somewhere. So we don't know how they ended up there. They were just plopped down. They're in area 9 to start. And then they decided to move to area 6 and fish in area 6. So for some reason, the fishing was better, probably in area 6 for that haul. Maybe the fish moved down there, someone called them up. They decided to move down there and fish. For scenario 2, abundance is still fixed, right? Darker area, more catches. Same in every single year for a given iteration of our OM. But now they can make multiple hauls. So they always start from area 1, but then we let them make multiple hauls according to some process where the average number of hauls is roughly 5, but it's stochastic. And then, so in this example sort of trip, they start in area 1, they decide to move to area 4, then they move to area 8, then they stay in area 8, fish again, move to 6, and end up in 9. And you can kind of see, compared to before, there are a lot of observations in area 1 because they always start there. There are a lot of observations in the areas where there are a lot of catches, but in other areas, especially where catches aren't so good, on average, we don't see as many observations. Scenario 3, we are finally getting to some more interesting ones. Here, abundance is random. So on the left-hand side is year 1, right-hand side is year 2. Abundance is random. I think we pull from a uniform distribution. We scale it such that it always equals the same constant, so it doesn't change over years. And then we scale it again according to what the abundance trend is in that year. So it follows a true abundance. Here, we also have a little bit of habitat, we'll call it. Essentially, what it does is make this area on the western side not visited by fishers. As you can see, there are very few observations in areas 7 and 8, basically because they have to travel very far and it's almost never worth it to them. They can still make multiple hauls and they still always start in area 1. Scenario 4, very last one, our abundance is going to exhibit a spatial trend. Here, 1, 2, 3, and 4 is we're following years over time, so 4 is later. And so a bunch of fish start on the west side in the beginning, and then they slowly move over to the east side over time. Fishers still always start in area 1. They can make multiple hauls, but as you can see, because of that habitat in the middle, that makes it very difficult to get over to areas 7 and 8. We really don't have many observations there, even though there are fish over there, right? So what this is trying to describe is a scenario where we don't get to see all of the fishery in our fishery-dependent data. So, some results. Scenario 1 and 2, again, recall, are when abundance is fixed. And so the uncorrected trend is basically some naive estimate of average catches, and these tend to overestimate what the abundance is. So 0 here would be 0 relative error, and then we tend to overestimate what abundance is over time because we keep seeing fishers catch a lot of fish because we only see them go to places when fishing is good. The blue line is randomly sampled fisher behavior. So it's a bit of a sanity check. Instead of following their preferences, let's say they just randomly chose where to go. And in some ways, this approximates if we had another fishery-independent survey, right? So if fishers weren't choosing where to go, they weren't selecting based off their preferences, but they were just randomly going anywhere, then there also wouldn't be any error if we use fishery-dependent data because they're not selecting. We see that the corrected index tends to perform pretty well for the fixed abundance. For scenarios 3 and 4, now we have random abundance and a spatial trend, and it gets a little bit more interesting. Maybe surprisingly, for random abundance, the corrected index still performs fairly well, although there's a little bit more uncertainty, where here it is the standard deviation over the root number of observations, I believe. And the intuition here is that the corrected index still performs well because when it's random, I'm basically just as likely to miss locations with high abundance as low abundance. So if we go back, so in some years here, basically there weren't even enough observations to estimate these areas. So I couldn't estimate the catches in these areas, but in some years are lower than average, and in some years they're higher than average. So it evens out in the end. The problem is when there's this trend. And when there's this trend, then essentially we can't estimate what we don't see. And there may be hopefully some points where we could bring together some methods in fishery science and economics here together. But in this particular model, if we don't see what's going on there, we can't estimate what the catches are. And so we also ended up overestimating catches over time or abundance over time. And again, the Samney check here, if they were randomly sampling, then there wouldn't be a problem because they would have ended up in that area, in the western area anyway, because they wouldn't care about travel and distance anymore. Perhaps unsurprisingly, if we then take those abundance indices and pull them through stock synthesis, here we have 4 different sort of data scenarios where let's say that we had a quadrennial fishery-independent survey, and then we ended the survey at year 88. Then the estimates of spawning biomass were pretty good up until 88, and then it kind of tailed off and uncertainty got really big. If we include bad data, such as uncorrected fishery data that overestimated abundance, well, then we would overestimate spawning biomass. Whoops. And then randomly sampled data is essentially the same as saying that we got another fishery-independent survey, which is great. So hopefully they would never just cut off the fishery-independent survey, but here we end up getting a second set of fishery-independent data, essentially. But we see that the corrected index can essentially can do the same thing for us in some of these scenarios, where this is from, sorry, I should have mentioned it earlier, scenario 2, because obviously the corrected data worked well. If it was scenario 4, we'd have problems. So, some things that we still need to investigate. One of the nice things about this model, we presented something that's fairly stylized, right? But for example, if we're looking at utility and it's just a function of catches, you might say they care about other things too. You could include whatever you wanted to in that utility function, right? So if they care about their target species, but they also care about bycatch, and you have data on bycatch, you should include that in their utility function, right? But maybe you don't know the fishery well and you've misspecified either the catch function or the utility function. It would be useful to see exactly what that impact was. We've done some work on investigating misspecification of the distribution of the error terms, but we're still working on that. We would like to investigate some additional data generating processes. We have 4 scenarios here, but there could be some other ones that might be interesting to assessors or others. I'd love to hear about that. As I mentioned, there are a number of existing standardization methods in the fisheries science literature. We saw that the scenario where we had the most trouble was basically when we didn't have any data in that area. And so there are these other models where essentially we get to extrapolate spatial distribution past based on some sort of assumption about how the decay and how the catches would behave over there. But we might be able to use some of these other methods in conjunction with what we're doing here. Because really what we've done is we're investigating a very specific type of error, right? Where there's selection in the data that we end up seeing. And our chosen correction is actually relatively straightforward. It's just this polynomial, like probability of selection plus probability of selection squared plus whatever you chose the dimension of the polynomial to be, right? And so it's fairly straightforward to just plot that onto any sort of linear catch equation. And so it might be useful to sort of see how we can use these methods in conjunction with existing spatial temporal models, where we certainly, I don't think this is a panacea for correcting this sort of fishery-dependent data, but for this particular type of selection that we've described here, we think it might be useful. And then finally, we've talked about abundance indices, but also we can think that fishery-dependent data is also used for age or length comp inputs into these models, so that might also be selected in some way. For example, if fishers want to catch bigger or smaller fish, depending on given year, depending on prices, anything else like that. So thank you, everyone, for listening. And I would be very curious to hear if there are any questions or comments, and I'd love to hear more. Thank you, everyone.
Hi, this is your host, Lisa from NOAA Central Library, and thank you for your presentation, Alan. That was great. Audience, we have about 15 minutes for questions, and we would love to hear them. So please type them in the Q&A chat, and I'll upload them for Alan. And remember, your first name will show up on the screen with your question, but you can ask questions anonymously. If you choose this, be aware that the speaker will not be able to follow up after the webinar. And one more quick reminder before we start with the questions. This presentation is being recorded and will be available on the NOAA Central Library YouTube channel later today, just in case you know someone who might be interested in watching the recording of Alan's presentation. So let me send you that link right now. And we did get a couple of questions, Alan, while you were speaking, so let me go ahead and start with this first one. This question asks, how essential to your results is the fisher's knowledge of beta J? Have you considered a specification where beta J is not known to the fishers or known with error?
Yeah, that's interesting. We have considered a specification where if you saw catch is known with error to the fishers. For example, the stochastic portion, they know some of it, and then there's this other stochastic portion that they don't know. So catches, they might think expected catches are big, and they ended up being smaller because that portion of the error, the realization went the other way. We haven't investigated anything specifically when the beta is not known. I'm trying to think of how that might differ. Especially, the outcome might be different compared to the stochastic portion being unknown. So that's something that I would have to investigate. I would say that for the catch equation where they don't know part of it, so they know catches with error because they don't know part of the stochastic portion, the general mechanism stays the same and the results are similar, but there's more noise because sometimes they're wrong, essentially. I think my intuition, and I'm kind of throwing something out there, the beta J being unknown, I feel like it'd have to be different in some systematic way in order for the mechanism to be different, right? If it was again like mean zero different, then I suspect the mechanism would be the same, but it's definitely worth investigating. So thank you for the question.
Thank you. This next question asks, says, I'm not a Bayesian, but this makes me wonder, how does this compare to treating the stock assessment as a prior and updating based on observed catches?
Treating the stock assessment as a prior and updating the stock assessment, I assume, based on observed catches. So, oh wait, sorry, that's a different question. Okay, so if I understand the question correctly, you're saying the results from the stock assessment are the prior, and then we're updating that with observed catches? I might be understanding the question a little bit.
I'll tell you what. I'll go on to the next question, and if Kevin wants to update us, go ahead and send something in the chat or send another question. This next question asks, when there is a spatial trend, would you assume that the same problem would arise with survey data as you found with fishery-dependent data, especially in the situation under changing climate regimes if the domain of the abundance shifts?
So in our, excuse me one second. Sorry, getting over a cold. In our example, our randomly sampled fishery sort of served as our proxy for another fishery independent survey, right? And so to the extent that if the fishery is changing, but are we still sampling all the areas? I think as long as we're still getting the total spatial extent, even if they're moving around, we should be okay, right? I think unless you're talking about a situation where they're moving outside of the survey extent as well, in which case, at least my initial intuition is we'd have the similar problem. So possibly we would need another method to extrapolate beyond what the where we have observations. Is my initial guess. Yeah, and again, this might be an area where we could use existing methods in the fisheries science literature that allow us to extrapolate over space.
Hi, actually, Kevin did respond in the chat, so I'm going to put his question back on the scene here and read what he said in the chat. His chat says, the probability distribution estimated in the stock assessment is the prior. One would update the entire probability distribution in light of the information contained on fishery data, such as CPUE, total catch, etc.
That's interesting. No, thank you for updating, Kevin. So the prior is a distribution from the assessment, and then you get these catches. So full disclosure, I am an economist. I am not an assessor. My knowledge of assessments here is probably poorer than most of you. I would think the type of error here. So I guess there's two scenarios. One where we're updating with catches that are corrected, and the other where we're just updating with catches that we observe without any sort of correction. I imagine if you just updated with uncorrected catches, you would end up with a similar problem, but I'm not 100% sure. I think the issue here at hand is still this selection that occurs and the selected sample of catches that are biased because they tend to fish where catches are good. I'm not sure you would get around that depending on just by, putting it into the stock assessment. But certainly if I am misunderstanding your question, I apologize. And if my understanding of stock assessments is very poor, I also apologize. This is exactly why you need stock assessor co-authors.
Awesome. Thank you so much. And thank you, Kevin, for clarification on that. It looks like that is our last question. So I'm going to move over into our thank you zone here. And I just want to say again, thank you for sharing your work with us, Alan. I really appreciate it. And for organizing this event audience, please join us again on the first Thursday of the month at 3 p.m. Eastern Standard Time for the next National Stock Assessment Science Seminar. And everybody, take care and enjoy the rest of your day.